All right, I had a question regarding problem 10 in the section 4.2 homework, which I thought was great because this particular problem really shows you the relationship when you're combining two functions together. So we have two functions, f, which is shown here in the blue graph. Let me go ahead and expand that out. So F is in the blue graph and G is the red graph. And they're wanting us to find four different combinations of functions. The first one they want us to find is F plus G at -4. Then they want you to find the composite function F composed with G at -3. Then they want you to find the quotient function F over G of -7. And then they want you to find the composite function G composed with F at -2. So let me open a blank PowerPoint slide. Okay, so let's first look at the F plus G at -4. So to be able to do F plus G at -4, I need to know what F at -4 is, and I need to know what G at -4 is, and then I'm going to add them up. So F plus G of -4 is F of -4 plus G of -4. Okay, so we're going to first look at the blue graph, and we're going to evaluate the function F at -4. So we're going to go over to -4 on the x-axis, and we're going to go up where it intersects the function F, and it intersects at 7. So F of -4 is 7. Then we're going to evaluate G at -4. So we're going to go over to -4 on the x-axis, and we're going to go up where it intersects G, and it intersects at 2. So the sum of those two numbers is F plus G at -4. So what did we get? We got 7 for F. We got 2 for G. So the sum of those two things is 9. So F plus G at -4 is F of -4, which is 7, plus G at -4, which is 2. 7 plus 2 is 9. Now the second one's a little more complicated. You're trying to find F composed with G at -3. So by definition, let's go over to our slide. By definition, F composed with G of -3 is F evaluated at G of -3. So I need to figure out what the value of G is at x equals -3, and then plug that in and figure out what F is at that value. So I need to go to my graph. I need to find out what G is at x equals -3. Okay. So go over on the x-axis to -3, go up where it intersects G, and what is that? 1? So G of -3 is 1. And so then I'm going to evaluate the function F at 1. So what do? I go over to where x is 1, go up where it intersects F is at 2. So can't do that. So f composed with g of -3 is 1. Oh, excuse me, 2. Because, again, g of -3, right there is 1. So we're going to evaluate f at 1. F at 1 is 2. So from my graph, g of -3 was 1. So we're going to evaluate f at 1. And from my graph, when x is 1, f was 2. Okay, then we're going to evaluate f over g, the quotient function, at -7. And this simply means to take f at -7 and divide it by g of -7. So evaluate what f at -7 is, evaluate what g at -7 is, and then take the quotient. Okay, so what's f at -7? So we're going to go -7 in the x direction, -7 right there, and we're going to go up where it intersects f. Is that 10? So f at -7 is 10. And then g at -7. Go over to -7, go up to g. Is that 5? So 10 over 5 is 2. So this was 10. That was 5. So that is 2. And then the last one is g composed with f of -2, which is g evaluated at f of -2. So I need to figure out what f of -2 is. So go back to my graph. F of -2. If I go to -2 and then go up, f of -2 is 5. So I'm going to evaluate g at 5. So I'm going to go over g to 5. If I go over to 5, and then I have to go down, don't I? So g at 5 is -7. Great problem. A great problem. Seriously, great problem. Thank you for asking about it. All right, let's do section 4.3. I don't want to be a nudge, but this is the easiest section in this book, so don't mess it up. So we're going to determine whether two functions are inverses. We'll talk about what makes a function one-to-one. We'll find the inverse of a function, we'll graph them, and then we'll find inverse functions on limited domains. All right, so what makes a function an inverse of a function? If you evaluate a function f at g of x and you get x, so you evaluate f at g of x and you get x for all the x's in the domain, and you evaluate g at f of x and you get x, those two functions are inverses of each other. And we denote the inverse of a function as f with a -1 in the exponent. That means the inverse of function f. For example, those two functions are inverses, which may be somewhat obvious to you, maybe not. But how can I determine if those two functions are inverses of each other? Evaluate f at g of x, which means in my function f, replace x with g of x. So it's g of x plus 3. That's how you evaluate a function at another function. But what's g of x? Is g of x x minus 3? What happens when I put x minus 3 in for g? Do I get x? Okay. What's g at f of x? We're going to evaluate g at f of x. So where there's an x, we're going to replace that with an f of x. But what's f of x equal to? It's equal to x plus 3. Is that it? Are those two functions inverses? So that's all there is to it. That's what makes two functions inverses of each other. If I evaluate one function at the output of another function and I get x, those two functions are inverses. Yes. Okay, so these two functions are inverses. The function that can be used to convert a temperature in degrees Celsius to Fahrenheit, we got this function, gosh, way back at the beginning of the semester. F of x equals 9/5 times x plus 32. The function that can be used to convert a temperature of degrees Fahrenheit back to Celsius is g of x equals 5x minus 160 divided by 9. Those two functions are inverses. To show that those two functions are inverses, you can evaluate f at g of x, and you can evaluate g at f of x. We're going to do that. So f of x is 9/5 x plus 32. G of x is 5x minus 160 over 9. So I'm going to evaluate f at g of x. So in my function f, where there is an x, I'm going to replace it with a g of x. So I get 9/5 times g of x plus 32. And then what's g of x equal to? I'm going to replace the g of x with what it is equal to, 5x minus 160 over 9 plus 32. So what happens here? Well, the 9's cancel. And will the 5 cancel? Cancel there. What's 160 divided by 5? Is it 32? So is that x minus 32 plus 32? Is that x? Okay, let's evaluate g at f of x. So in my function g, where there's an x, I'm going to put an f of x. So is that going to be 5 f of x minus 160 over 9? So where there's an x, I replace that with f of x. So we get 5 times, what's f of x? Is it 9/5 x plus 32? Minus 160 over 9. Oh, we're going to have to do a little arithmetic simplification here. Okay, so I have 5 times 9/5 plus 32 divided by 9. The 5 will cancel here. So I get 9x. And then I'm going to distribute that 5 across the 32. That's going to be plus 160. Minus 160 over 9. Is that 9x over 9? Is that x? So those two functions are inverses of each other. And I can prove that they're inverses of each other by looking at the two composite functions. F composed with g of x, or f evaluated at g of x, and g composed with f of x, or g at evaluated at f of x. If both of those things are x's, or x, then those two things are inverses. So an inverse function undoes what the other function does. So if f takes that function, multiplies it by 9/5, and then adds 32, then g's got to do the exact opposite. So you go from one function to g and then back, you have to end up back at x. So what one function does the other function has to undo it. That's what functions do. Inverse functions do. So two functions that are inverses undoes what the other function does. Okay? And we'll talk about that more in a minute when we look at ordered pairs. A function f is a one-to-one function if each output of the function corresponds to exactly one input in the domain of the function. Well, that's kind of confusing. This means there's a one-to-one correspondence between the elements of the domain and the elements of the range. Okay. In a function, I can have an x go to a y. I can have another x go to the same y. So I can have two x's go to the same y. I can have two inputs go to the same output. That's okay. That's a function. So this is a function. I can have some x1 go to y. I can have some x2 go to the same y. That's fine and dandy. That is not one-to-one. It is not one-to-one because a one-to-one function, I cannot have two different x's going to the same y. That is not a one-to-one function. Okay? So what makes it one-to-one? Each x has to go to a unique y. You can't have the same x, two different x's going to the same y. So you can't have two things mapped to the same output. Okay? So are these functions one-to-one? This is not. How do I know that? The easiest way, are y'all listening? Easiest way to do this is evaluate this at -1 and +1. So what's f of 1? Is that 3? What's f of -1? No, it's 3. Because what's -1 raised to the 4th power? 1. So is that one-to-one? No, because you can't have two different inputs going to the same output. Not one-to-one. Is this one-to-one? Is that -2? What's f of 1? Is that 0? Are you good? So is this one-to-one? Yes. Is this one-to-one? No. Now, the easiest way to tell if a function is one-to-one is to graph it. Okay, it's called the horizontal line test. Now, if you recall from way back in the beginning of the semester, we had what is called a vertical line test. And a vertical line test tells us whether or not a graph is a function. If you can draw a vertical line through it and not hit the graph more than one place, it is a function. The horizontal line test tells you if it's one-to-one. If you can draw a horizontal line through it and hit the graph in more than one place, it is not one-to-one. It still might be a function, but it's not one-to-one. Okay, I'm going to real quick graph these. Excuse me. I think it's either allergies or I'm coming down with something. I'm not sure. All right, so I'm going to graph 3x to the 4th. So 3x raised to the 4th power. And I'm going to go back and do a standard window. So I'm going to do zoom 6, because who knows what my window is. Okay, that is a function. It passes the vertical line test. It is not one-to-one, because if I draw a horizontal line through it, I can hit the graph in more than one place. So I have two different x's going to the same y, not 1 to 1. Okay, how about the other one? Was that x to the third minus 1? I'm probably shouting because I don't have my hearing aids on, so I can't hear how loud I am. Okay, so let's graph that. That is 1 to 1. I can draw a horizontal line through it and not hit the graph in more than one place. So vertical line tests are for if the graph is a function or not. Horizontal line test is the function 1 to 1 or not. If you have two functions and they're inverses of each other, then this is kind of unique. Okay, there's a problem on your exam that you better not get wrong. Wagging my finger at you. Because what is true about two functions that are inverses? If you have a function f and you have an ordered pair AB that satisfies f, so AB is a point on the graph of f. If you have a function g that is the inverse of f, then a point on G must be BA. So what does a function and its inverse do? It interchanges all the ordered pairs. That is what it does. So it takes the input of one function and makes it the output of the other. It takes the output of one function and makes it the input of the other. It interchanges the ordered pairs. That is what it does. The domain of the function f is the range of its inverse, and the domain of the inverse is the range of the original function. It interchanges the domain and range. Excuse me. All right. How do I know if it has an inverse or not? I know it has an inverse if it's 1 to 1. I know it's 1 to 1 if it passes the horizontal line test. So I've already graphed this. F of x equals x to the third minus 1 is 1 to 1, so it has an inverse. I have a function. I can graph that function. If I can draw horizontal lines through it and not hit the function's graph in more than one place, that function has an inverse. It is 1 to 1. All right. So let's verify that the cube root of x plus 1 is the inverse of f of x equals x to the third minus 1. So let's see if we can't do that. So for functions to be inverses, f evaluated at g of x must be x. So we're going to evaluate the function f at g of x. So we're going to replace the x with g of x. So we're going to have g of x cubed minus 1. But what's g of x? G of x is the cube root of x plus 1, and we're going to cube it. What happens when you cube a cube root? Does the cube root go away? So is that x plus 1 minus 1? Is that x? Okay, we're going to evaluate g at f of x. So in my function g, we're going to replace the x with f of x. So we are going to take the cube root of f of x plus 1. But what's f of x equal to? Is it equal to x to the third minus 1? What's x to the third minus 1 plus 1? Is that x to the third? What's the cube root of x to the third? So are those two functions inverses of each other? All right, what's the domain and range? What's the domain of f? Is there anything you can't cube and subtract 1 from it? So is the domain the set of all real numbers? So what's the range of G? So whatever the domain of f is, that's the range of G. But what's the range of f? Is it also the set of all real numbers? So what's the domain of G? There's nothing I can't cube. There's nothing I can't add 1 to take the cube root of it. You can take the cube root of any positive or negative number. All right. How do you find the inverse of a function? So you're given a function and you're told to find the inverse of it. Here are the steps to do that. Step number 1 is to take the function notation f of x and make it a y. So replace f of x with y. Then what does a function and its inverse do? It interchanges the domain and range. That's what they do. So you take the x and you make it a y. And you take the y and you make it an x. So you interchange x and y. And then you solve for y. So what's the inverse of this function? Step number 1. So we're going to write this as y equals 2x minus 1 over 3. Step number 2, I'm going to write it the way you're doing. Interchange x and y, because that's what an inverse does. So we're going to make the y an x and the x a y. Now solve for y. Now that might task you a little bit, but it shouldn't. We've been doing this since the beginning of the semester. So what would you do? You're solving for y. So what's the first thing you do? That's what I would do. Then what would you do? That's what I would do. Then what would you do? Then replace, this is step 4, replace y with f inverse. They do exactly the opposite of each other. All right, for example, evaluate f of 1. F of 1 is what? 2 minus 1 over 3. Is that 1/3? If I put a 1 in right there. 2 minus 1 is 1. 1 over 3 is 1/3. Okay. What if, didn't leave myself a lot of room here. What if I evaluate this at 1/3? 3 times 1/3 is 1. 1 plus 1 is 2. 2 divided by 2 is 1. So what do? Exactly the opposite of each other. You input 1 in f, you output a third. You input a third in f inverse of x, and you output 1. They do exactly the opposite. Isn't that cool? That's why you're not going to get that problem on your test incorrect. Because what does a function and its inverse do? It interchanges the x's and the y's. That is what it does. Now, what if I were to, well, That's the second part of this problem. So let's find the inverse of this function, and then let's graph it. Let's graph the function and its inverse. So step number 1, replace f of x with y. Okay. Step number 2, interchange x and y. Okay. Step 3, solve for y. So what do we got? So what would be the first thing? Multiply by 5. Add 3. Divide by 4. Replace the y with f inverse. Okay. If I input 1 here, f of 1 is what? A fifth? 4 minus 3 is 1. 1 over 5 is a fifth. If I input a fifth right there, what happens? 5 times a fifth is 1. 1 plus 3 is 4. 4 divided by 4 is 1. So do they do exactly the opposite of each other? Let's graph them. Okay, so let's graph f. And I'm going to use my fraction. So alpha y equals number 1. And f is what? 4x minus 3 over 5. 4x minus 3 over 5. And then let's graph the inverse. So alpha y equals number 1. 5x plus 3, 5x plus 3 over 4. Okay, I'm going to graph a third line. I'm going to graph y equals x. What do I see about the function and its inverse? So the black line is y equals x. Can you see symmetry about the line y equals x? Can you see that symmetry? Does it divide those two lines exactly in half? Is this distance equal to this distance? Is this distance equal to this distance? If I evaluate, well, it's kind of hard to do that, but if I evaluate the, well, let's talk about that. The blue line goes through 1, 0. The red line, which is the inverse, goes through 0, 1. Is that a coincidence? No, because they're inverses of each other. So blue goes through 1, 0. Red goes through 0, 1. Is there anything else we can see? Those, it's kind of they're kind of odd functions because they're fractions, so it's a little bit difficult to see the rest of that. But if two functions are inverses of each other, they are symmetric about the line y equals x. And that should aid you when you're doing your homework or when you're doing a problem on the test to determine which of the graphs are graphs of the function and its inverse. Okay, so are those two functions inverses of each other? Yep. Are they symmetric about the line y equals x? Yep. If I have a point up here, do I got a point down here that's the same distance away from the line y equals x? The blue function goes through 0, -2. So the red function has to go through -2, 0. Has to. No choice. Oops. Don't know what I'm doing. Okay. All right, let's do an example. If $1,000 is invested for 3 years at an interest rate X compounded annually, the future value Y of the investment is given by Y equals 1,000 times 1 plus X to the third. So what that means is that's how much money you have in the future if you invest it at this particular interest rate. And you're investing for 3 years. So whatever that interest rate X is, you plug that into the formula. That'll tell you how much money you have after 3 years. To find the interest rate that results in a future value Y, to do that, we're going to find the inverse. So when we find the inverse of this function, that will be in terms of the interest rate. So the original function is the future value, and it depends on the interest rate. The inverse is going to be the interest rate depending on whatever your future value is. Use the inverse function to find the interest rate that gives a future value of $1,331 in 3 years. Okay, so this is a function that gives me a future value that depends on the interest rate. So the independent variable is the interest rate. The dependent variable is whatever this is worth after 3 years. So if I find the inverse, the independent variable is going to be the future value. What's going to be dependent on the future value is the actual interest rate. So let's find the inverse. So step number 1, replace f of x with y. Step number 2 is interchange x and y. Step number 3 is to solve for y. Now we got a conundrum. How do you solve for y? What would you do? I got y inside parentheses being raised to the third power. Any clue? Anybody? Anyone? What do you want to try? Do you have a root property that you can take the same root of both sides of an equation? If it's an odd root, you don't have to put any plus or minus in front of it. If it's even, you do, but if it's odd, you don't. So can I take the cube root of both sides? Can I divide by 1,000 and then take the cube root of both sides? Does anybody know what the cube root of 1,000 is? How do I know it's 10? Got 3 zeros. 10 times 10 times 10 is 1,000 because you got 3 zeros. So if I take the cube root of something with 3 zeros and a 1, it's got to be something with 1 0. So if I take the cube root over here and the cube root over here, what happens if I take the cube root of a cube? So is that the cube root? The cube root of x over 10? cube root of x is the cube root of x. The cube root of 1,000 is 10. Is that equal to 1 plus y? Now, do you subtract 1? So is that the inverse? Cube root of x divided by 10 minus 1? So what does that find? That finds the interest rate for a particular future value. So if I know how much my money is going to be worth in 3 years, I can figure out what interest rate that I've invested it at. Or if I know how much money I want in 3 years, can I plug that in and figure out what interest rate I need to invest it at? Now, whether you find an investment that has that interest rate is a whole nother ballgame. But if I know what I need, for example, you're going to pay, let's say in 3 years, you're going to take a trip to Europe because you're going to graduate from college and you're going to, woo! If I know how much money I need to take a trip to Europe, can I figure out what interest rate of a particular value that I need to invest? Sure. Find the interest rate that gives a future value of $1,331. So we're going to evaluate this inverse function at 1,331. What's the cube root of 1,331? How do you find the cube root on your calculator? Math? Math number 4? Is it 11? So math number 4 is the cube root. We're finding the cube root of 1,331, which is 11. So is that 11 over 10 minus 1? So that's 0.1. How do you determine what the interest rate is? Do you multiply that by 100? To get from a decimal to a percentage, do you multiply by 100? So is that a 10%? And that's unheard of. Where you're investing money. Can you imagine investing at 10%? Yes, sort of. The formula is a little more complicated than that because you also have a present value you got to stick in there. And what were we investing? We were investing $1,000. So if we changed how much we invest other than $1,000, you'd have to change that. But yes, if it were 4 years, all you'd do is raise it to the 4th power. You'd have to take the 4th root of 1,000 though. Does that make sense? And that's, I don't know what that is. Something less than 10. Okay, let's go ahead and do this one. And time permitting, I do want to start section 4.4, just so that we don't have to do all of it on Monday, and maybe get you out of here a little early on Monday so you can go start studying for your test. Because your test is a week from today, unfortunately. These chapters are so short. They're only 4 sections long. That's 4 days. So they come real quick, don't they? Because of friction from the walls of an artery, the velocity of blood is greatest at the center of the artery and decreases as the distance x from the center increases. So you got an artery, which is a tube, and the distance you are from the center of the artery, that decreases the velocity. So the velocity of your blood is the highest at the center of your artery. And then as you move closer and closer to the artery walls, the velocity of your blood slows down. The non-negative velocity in centimeters per second of blood corpuscle in an artery can be modeled by the function v for velocity is k times r squared minus x squared, where r squared is the radius of your artery and x is the distance you are from the center. K is a constant that is determined by the pressure, the viscosity of your blood, and the length of the artery. In the case where K is 2 and R is 0.1 centimeters, so whatever pressure is and all that good stuff, K is determined to be 2, and then the radius of your artery is 0.1 centimeters, which is pretty small. The velocity can be written as a function of the distance x from the center as v of x is 2 times 0.01 minus x squared. And since r is 0.1, r squared is 0.1 squared, which is 0.01. Assuming that the velocity is non-negative, and one would assume that your blood's not flowing backwards, that might be a problem. Does the inverse of this function exist on a domain limited by the context of the application? What is the inverse of the function? What does the inverse function mean in context of this application? Okay, part A. Assuming the velocity is non-negative, which means that velocity has to be greater than or equal to 0. So you can't have a negative velocity of blood flow. Does the inverse of this function exist on a domain limited by the context of the application? So since this is the range of my function, that the velocity has to be greater than or equal to 0, that is going to be the domain of my inverse. So in this case, x would have to be greater than or equal to 0, which makes sense. Because it makes sense that my artery, if I'm looking at an artery that has a diameter, a radius of 0.1, that the distance x would have to be positive from the center of the artery to the wherever I am in the artery's whatever position I'm in, and that would have to be positive. So it makes sense in the context of this problem. Also, since x has to be greater than or equal to 1, here, greater than or equal to 0 here. This is a parabola that opens down. And I know it opens down because I have a minus right there. So that opens down. And that is 1-to-1. If I only look at half of a parabola, that's 1-to-1. And since it's 1-to-1, it has an inverse. So it's all good. Find the inverse. Okay, step number 1. Replace v of x with y. Step 2, interchange x and y. Step number 3, solve for y. Now, if it were me, I'd probably go ahead and distribute the 2 across. And then I'm going to do a little finagling here. I'm going to move the minus 2y squared over to the left by adding it. And I'm going to move the x over here by subtracting it. And I still have to divide by 2. So we're going to divide by 2. And then we're going to take the square root. And are we all awake and listening? Typically, I would have to put a plus or minus in front of this. But we're talking about a distance in an artery. That's what y represents. If the original function, the input was the distance and the output's the velocity, in the inverse, the input is a velocity and the output is a distance. That is what it is. They interchange each other. So if they interchange each other and this function y is now a distance, it is a distance. That is what it is. It's the distance we are from the center of this artery. Since it's a distance, it has to be positive. So you don't have to put the plus or minus in front of it. So the inverse, f inverse of x, is the square root of 0.02 minus x over 2. This is the distance from the center of your artery. That right there is the velocity. So the original function found the velocity in terms of the distance you are from the center of the artery. X is the distance. V of x was I guess we should have used V of x, shouldn't we? Should have used a V there. The input was the distance, the output was the velocity. The inverse, V inverse of x is the distance from the center of the artery, and the input is the velocity. I got 20 minutes. I got forever. Oops, that's not what I want. This is problem 9 on your exam. Well, your exam, the numbers are jumbled, but this is on the review. If you get this problem incorrect, I'm going to yell at you. I've got inputs and I got the outputs of a function. Then I have the inverse. I have the inputs for the inverse and I got the outputs. So if the input is -2, what's the output of f of x? Is it -12? Because what do? Do they interchange each other? So if the output of the inverse is, excuse me, if the input of the inverse is negative 12, is that the output of the function? Are you listening? If the input of f is negative 1, what is the output? Is it negative 8? If the input of the function 0, what's the output? Is it negative 4? If the input of f is 1, is the output 0? If for the inverse is negative 12, negative 2, negative 8, negative 1, negative 4, 0, 0, 1. Everybody better get that one right. All right. Solving equations. Now, a lot of the equations in this section you can solve graphically. Anything that we show you an algebraic method to, you can use a graphical method for. Graphical methods work really well if the solutions to the equation are integers or simplified fractions. If they're radicals, then it gets a little bit dicey. So we're going to solve radical equations, equations with rational powers, equations that are quadratic in form, quadratic inequalities, you need to graph those. Power inequalities, you need to graph those. Inequalities involving absolute value, I recommend you graph those. Okay? Solving radical equations. An equation containing a radical can frequently be converted to an equation that does not contain a radical by raising both sides of the equation to an appropriate power. For example, an equation containing a square root radical can usually be converted by squaring both sides of the equation. It is possible, however, that raising both sides of an equation to a power may produce an extraneous solution, a value that does not satisfy the original equation. For this reason, when you solve equations that contain radicals, stop looking at your phone and look at me. When you solve an equation that contains radicals, you have to check your solutions, because some of your solutions may be extraneous, which just always floors me. That you could have, you solve this, you go through all this, and that's not really a solution. Let's show you what I mean. To solve a radical equation, you isolate a single radical on one side of the equation, then square both sides, or raise it to whatever the index is. If you've got a cube root, you cube it. If it's a fourth root, you raise it to the fourth power. If a radical remains, repeat steps 1 and 2. Now, if a radical remains, you're going to graph it, by the way. Solve the resulting equation. And then check your solutions. Solve the radical equation. The square root of x plus 5 plus 1 equals x. Step number 1, isolate the radical. Which means I need to get that 1 over there. So I subtract it. Step number 2. Since I have a square root, I'm going to raise both sides to the second power. What's the square root of x plus 5 squared? X plus 5. That is correct. What is x minus 1 squared? X minus 1 times x minus 1. Very good. Which is what? X squared minus 2x plus 1. Got to FOIL it or use the formula for the squaring a binomial, whatever you want to do. Now what do I do? I agree. Because it's a quadratic, and it's quadratic because it has an x squared in it. So I need to get the quadratic on one side and 0 on the other. Now, can you solve this by factoring? Can you solve this by using the quadratic formula? Can you solve this by graphing? Whatever floats your boat. I'm going to factor it. And I'm going to put the 0 on the right because it just bugs me when it's on the left. So I need two factors of -4 that add to -3. No. 4 and 1. There you go. So we get what? -4 plus 1 is 0. So do we get 4 and -1? One of those is not a solution. Which one? Why is the negative not a solution? Because it doesn't work. If I put in -1 for x, what happens? Well, over here on the right-hand side, I get -1. That's not going to happen. There's no way I can take the square root of something and then add 1 to it and get a negative. Not going to happen. This is extraneous. That is the solution. Now, why does this happen? You may not care, but there actually is a reason why this happens. So would you agree that 2 is not equal to -2? Would you agree? Correct? 2 and -2 are not the same number. Would you agree? But what happens if I square both sides? Well, there's a problem. So when you square both sides or you raise both sides of an equation to an even power, that can happen. So you can introduce an extraneous solution. If you raise both sides to an odd power, you're good to go. But if you raise both sides to an even power, you have to be careful and you have to check your solutions. You can also graph this. So I'm going to graph the square root of x plus 5 plus 1 on one side in 1y1, and I'm going to graph x in the other graph. So in y1, oops, let's get rid of that. In y1, I'm going to graph the square root of x plus 5, second square x plus 5. I got to arrow out of that radical. I'm going to add 1. And in y2, I'm going to graph x. Do they intersect only in one place? One solution? So where do they intersect at? 4. 1, 2, 3, 4. So you can see from the graph that these two functions don't intersect at two places. Is -1 a solution? No, because they don't intersect at -1. And honestly, I don't care how you solve this, whether graphically or algebraically, even though the problem might say solve this algebraically, I don't care. You're in a functions and modeling class that's highly dependent on your calculator. So if you can use your calculator to solve an equation, should you use your calculator? Sure. You have that capability. That's kind of what this class is modeled on, using your calculator to solve problems, correct? Or using graphical means to solve problems. How about this one? I absolutely positively guarantee you, you do not want to solve this algebraically. If it's got two radicals in it, just throw up your hands up and say, nope, not gonna do it. So what are you gonna do? You're gonna put this in your calculator and see where these two things intersect. Okay. If it's got two radicals in it, wait till you get to calculus and then solve it algebraically. And even then you don't need to, because you can solve this graphically. So I'm going to put the square root of 4x minus 8 minus 1 in y1. I'm going to put the square root of 2x minus 5 in y2 and see where they intersect. So on the left-hand side of the equation, we had the square root of 4x minus 8. Arrow out of that radical, and then we had minus 1. So that's the left-hand side of the equation. What was the right-hand side? Was it the square root of 2x minus 5? Look good to you? Kind of hard to see where they intersect. It looks like they're intersecting at 3 to me. Does that look like to you, 3? I can zoom in right there and see they're not intersecting beyond that because they're both kind of going like this. So they're intersecting right in here. And it does look to me like at one place and it's at x equals 3. So I'm going to zoom in. So I'm going to go zoom. I'm going to zoom in number 2. And I'm going to zoom in right around that place. So I'm going to go over here and go up. Yes, it is at 3. Now you can calculate the intersection too. Do second calc number 5.
I don't know if you can fix this for me.
It's 3. What'd you do to it?
I didn't get to
Do a zoom. 6. Fixes everything.
wait, Zoom 6?
Zoom 6 changes your window back to standard.
Oh,
Yeah. Cool. Zoom 6.
3.00.
Round it. It's because of our guess. See, if your guess is not perfect, it's going to round it. It's going to give you an estimate because it uses an iterative process to get the answer. But 3.00000 is 3. 2.999999 is 3. And you seem to think that's a good place to stop. So I guess this is a good place to stop. And it is a good place to stop. Are there any questions? This is really easy to solve with your calculator, by the way. Super easy. Any questions? All right, we'll finish this up on Monday.
What could I, is there anything I could do? But I thought I had ended up.
I will, let me write myself a note and I will open that up for you. Okay?
Do it.
Yeah, so you can do it. It's in the review class. Save on, and it's like the chapter 3 quiz, right?
Oh, no, the review.
Well, it's called the review quiz or something like that. But it's the chapter 3 review
It was in the review class, right?
Yes.
Um,
They do something quick for you.
Just want to say that I'm sorry for not showing up on Monday and showing up a little bit late
Okay.
today.
Thank you for apologizing. I appreciate it.
It is a quiz.
Yeah, in the review course. Yeah, because I just gave you a 0 this morning.
I see that.
So I'm glad you noticed.
That hurt my heart.
I will open it up and you can do it by
So this
Monday.
wasn't the review though. This wasn't like, cause I know
It is.
I had to do a review to get to the test, cause
That's a different, so you got two classes. You got the 10 o'clock one,
yeah.
you got the 11 o'clock one. In the 10 o'clock one, the review is just over the review stuff. In the 11 o'clock one, you have to do the review for the exam before you can take the exam.
Okay,
So
so
two, it's
this-
kind of confusing. One's a review quiz and the other's a review homework.
Okay. All right. Well, I'll do it today.
Okay, I will open it up as soon as I get back to my office.